Welcome back everyone to this next series of lectures, which we're going to call the Full Artificial Neural Network Regression Code Along. And this is just going to be an introduction about what these next couple of lectures are about. We just saw how to create a very simple artificial neural network work extremely well on the iris dataset. However, the iris dataset isn't a really realistic dataset. While it is real and it is a real dataset based off real flowers, it's a very convenient dataset, which is why it's used so much in tutorials on machine learning. Everything is a continuous numerical feature. There's only 4 columns. There's no categorical data. There's only 3 classes, and you don't really need to do any sort of feature engineering or much work on it at all. And in fact, the features are all in the same kind of number range or in the order, so you don't actually even need to do any sort of normalization. What we're going to do is we want you to be able to apply the skills of PyTorch and an artificial neural network to any tabular data set that you would encounter in your real work. So we're now going to try to give you the skills to be able to apply an artificial neural network to any tabular data set, regardless if it has things like date time information or categorical data, etc. So we want to use a realistic data set that contains both continuous and categorical data. And by the end of this series of lectures, you should be able to then swap in and apply an artificial neural network to your own classification and regression tasks. You can think of this notebook that we're going to go through as essentially a framework for you to follow when you're dealing with your own tabular data sets. We're also going to cover important topics like feature engineering, feature encoding, embeddings, dropout layers, and more. So really, there's a lot to learn in this next series of lectures. There's going to be quite a few of them, but we'll try to break it up into manageable chunks for you. So our data set is from a Kaggle competition, and there were originally 55 million records in this competition. However, for download and training time purposes, we've gone ahead and reduced this to 120,000 records, which is still quite a lot of records, but if we gave you all 55 million, it would take a super long time to download all that, and we have limits on how much we can upload to the platform. And also, if we gave you all 55 million, it would just take forever to actually train your network. So we reduced it to 120,000, still a ton of data to work with, and it should be fine for our purposes. So that Kaggle competition contained a lot of data about taxi rides. And the data contains taxi information such as the pickup date and time, the latitude and longitude, that is the actual GPS coordinates of the pickup and drop-off location, as well as the number of passengers that took that taxi ride. And when we're seeing this sort of data, we always want to be thinking of what could be useful information. And the idea of the competition is, given this sort of field of data, can you actually predict how much the taxi is going to charge for that particular ride? And we want to be thinking of different things like, does the actual time of day matter? Is it a big difference if it occurred in the AM or in the PM? And does the day of the week matter? Is there a difference between something like a weekend or a weekday? And also, we have to keep in mind things like longitude and latitude. Those are really specific things that a network may not be able to actually pick up on. So we want to be able to determine things like feature engineering. Are we able to determine the distance traveled from pairs of GPS coordinates? And how do we actually do that? So as I mentioned, we have to keep in mind that an artificial neural network can really only take in straight numerical data. And it's not going to be able to understand direct complex data, such as a full date timestamp. So a full date timestamp contains as a string code, or at least it looks kind of like a string code, things like the year, the month, the date, the hour, the minute, the second. A network just can't take in that data raw. What you need to do is you need to use feature engineering to separate it out into useful components. Things like AM versus PM, or the hour of the day on a 24-hour clock, so then it's a value between 0 and 24. So you don't have the convenience of being able to just feed in raw data like that with an artificial neural network. Instead, we have to perform some sort of feature engineering. And we need to do the same thing for things like longitude and latitude measurements. You could try to just pass those in their raw format, longitude and latitude, but then you'll have to have a really large network because the network would have to try to learn the relationship between longitude and latitude. And then there's the added complexity of latitude and longitude. Since it's determined on the equator, there may be issues with things being positive and negative. And also then you have issues of things like the actual resolution of that latitude and longitude. If you're doing all your pickup and drop-offs within the same city, the essentially the accuracy or significant digits beyond that decimal point are going to be really substantial because latitude and longitude doesn't change much within the distance of a city. You're looking at changes of maybe 0.001 scale. So you have to keep that in mind, and because of that, you'll have to do some feature engineering, and we'll show you how to do that to convert latitude and longitude into something like a distance traveled measurement. So let's go ahead and cover the steps that we're going to be doing throughout these lectures. First, we'll go ahead and read in the data. As I mentioned, we're reading in the data that we provided for you, that 120,000 records. We won't officially support reading in 55 million records because that's really dependent on your particular hardware. And I wouldn't suggest that you go and just do all 55 million. Instead, 120,000 records that we provide for you here is more than enough to get a feel of the realistic data set. Then, after reading in the data, we'll perform some feature engineering, things like calculating the distance based off latitude and longitude, as well as deriving useful date and time statistics, like AM versus PM. Okay, and then we'll also have some categorical data to deal with, so I want to show you how to deal with that, things like embeddings. And then what we're going to do is we're going to develop a tabular model class. So previously we developed just a simple model class that had in its attributes for a number of hidden neurons and then the feed forward process. And what we're going to do is we're going to expand on this in order to deal with both continuous data and categorical data that's within the same data set. And then once we actually create that tabular model class, after that, it's pretty much the same as we did last time. We add in the loss function and optimizer, do a train test split on the data, train the model, evaluate on test data, and then predict on brand new data. All right, let's get started. I'll see you at the next lecture.